All right, everybody, let's get started. So if anybody's got $800,000 burning a hole in your pocket, you can buy a hover bike now. All right, so there are two notebooks for today. There's one on permissions, and there's one on streams. I don't think we're going to finish the streams one today. I think you need to know the information in both notebooks in order to complete the assignment, though. So let's see what we can do. I'm going to work from PowerPoint for a lot of this lecture because the concepts I need to convey, it's just easier to show you in pictures. But the notebooks are complete, so they do contain all of the information that I'm going to talk about in the slides. And I'll post the slides after class. Okay, so file permissions. So Unix as an operating system was designed at a time when not everybody had their own computer. So what would happen is you'd have one computer and then you'd have multiple users on the same system at the same time. So they were designed for what are called multitasking and multi-user systems. And this is because owning your own computer was very expensive, right? So instead what you do is you would have basically what was a dumb terminal, and you would remotely log into a computer workstation. Sorry, you'd remotely log into a computer and there'd be multiple users on the system at the same time. Now, in order for this to work, there have to be mechanisms in place that protect the users from other users, right? Similarly, you have to protect the operating system from regular users, right? So for example, one user should not be able to modify the files belonging to another user unless they're specifically given permission to do so, right? You might not it might be the situation that you shouldn't even be able to see somebody else's files, right, depending on how the system is set up. And it certainly should be the case that a normal user should not be able to modify an operating system file, right? So for example, the typical user should not be able to go into the root directory and delete the root directory. So Unix created this notion of what are called permissions, right? So a user is allowed to own files or directories, right? So on your own computer, you own your home directory and all of the files inside your home directory. Most of you probably have administrator privileges on your operating system, so you actually own all of the files in your operating system. The owner has control over access to the files that they own. Right? So in Unix, if you're the owner of a file, you're allowed to change the permissions associated with that file. Right? So in other words, you're allowed to allow other users to see the file, to write to the file, or to delete a file. Similarly, you're allowed to grant other users the ability to delete or create directories in your own directories. Okay, so there's also this notion of things called groups. We're not really going to talk about groups in this course because you basically need to be a system administrator to create one. But there's another level of permissions called the group permissions that we'll see shortly. We're not going to use them a lot though in this course. Okay, if you want to know information about a user on the system, there is a command called ID. Right? So ID followed by your username will give you information about your your user identity. Right? Again, not especially useful for us in this course, but if you want to try it out, go ahead and do so. So a user has control of 3 different access rights on their files and directories that are owned by them. So a user can control read access, write access, and what's called execution access on files and directories. Right? So a user can adjust 3 different permissions. Okay, so these are what the access rights give you. So the access rights, if they're applied to a file, have a different meaning than the access rights applied to directories. Right? So let's just look at regular files. Okay? So if you have read access on a file, that means you can open the file and read the file. Right? If you have write permission on a file, that means that you can write to the file or truncate the file, basically make the file smaller. Right? Now, the interesting thing is in Unix, if you have write permission on a file, that does not automatically allow you to delete or rename the file. right? And that all has to do with the way that the Unix file system is created, right? So remember that in the file system, in the Unix file system, deleting or renaming a file, right, requires you to change a directory entry, right? Because the file name is part of the directory entry, right? File names live in the directory. They're not directly associated with any given file, right? So in order to delete or rename a file, you actually need write permission on the directory, right? It's not the file that you need the permissions on. And finally, if you have execute permission on a file, that lets you treat the file as though it were a runnable program or script, right? So in other words, you can use it as a command if you have execute permission on the file. All right, now what about directories? So if you have a directory, then read access on the directory allows you to list the contents of the directory as long as you also have execute permission on the directory. So execute permission on a directory means that that user is allowed to enter that directory using CD. Right? So CD into the directory name, that only works if you actually have execute permission on that directory. Right? Assuming you have execute permission on the directory, then you can also list the contents of the directory if you can read the directory. Right? Now, if you can change into the directory and if you can write to the directory, that's the thing that lets you change file names. Right? So that allows you files in the directory to be created, deleted, or renamed. Right? All right, so we know what touch does. We know what makedir does. We know what ls does if you use the long listing. So what exactly does the long listing tell you when you use it? So the long listing, you end up with output that looks like this with ls. Right? So the things over here, these are your permissions. The first thing, there's a hyphen, right? So the very first symbol is the file type associated with that file right there. So the first symbol can have one of the following. It can actually have more than these. These are only the common ones. So that first symbol can be one of these 5 things. There's actually more, sorry. So if you see a hyphen in the first position, that means that the file is a regular file, right? So it's just a file that probably contains text, right, or bytes. Right? If there's a D, then it's a directory, right? So if we just pop into, where is here? Oh, sorry, here. Okay. So if we pop into our into Linux. So this is the home directory of the virtual machine, right? You can see that there are no files here. There are no regular files in the home directory. There's a directory here called CISC220. There's a directory here called CISC220, right? So notice that their first symbol, in all of the cases in this directory, they're all start with the letter D, right? If I list everything in the directory using A, right, and then we'll see that there's a bunch of hidden files as well. So anything in white is a regular file. Right, so there's a file called .bashrc, right? And you'll see at the front here, there's a symbol. It's a hyphen, so that indicates that's just a regular file. Right? It doesn't look like there's anything else, any other file types in this directory. So let's pop back to PowerPoint. Right? If you see an L, that indicates a symbolic or soft link. Right? If you see something like a C or a B, which you shouldn't see in your home directories, these are what are called character special files and block special files. So if you see something with a C beside it, that indicates a device that can handle data as a stream or bytes. For example, if you found the file that corresponds to your terminal in Linux, then you'd see that there's a C beside that file. A block special file is a device that handles data in chunks of data, in chunks called blocks. So those are things like your disk drive. So if you found the file that corresponds to one or more of your disk drives on your file system, you'll see that there's a B beside it. Okay, now what about the next set of symbols? So the next 3 symbols, those are the read, write, and execute permissions belonging to the current user. Right? So read, write, and execute permissions belonging to the current user. So if there's an R, right, that says that the current user has read permission. Right? If there's a W, that says the current user has write permission, and if there's an X, the current user has execute permission. If there's a hyphen, then there are no permissions on that file. Right? So here RW hyphen means that the user, me, right, has read permission on file1.txt. I have write permission on file1.txt. I do not have execute permission on file1.txt. Right? So in other words, file1.txt is not a runnable program. Right? So that's the user permissions. Now, the next set of 3 are another set of permissions belonging to a different class of users. And then the final 3 are another set of permissions belonging to yet another class of users. Okay, so the next 3 are the permissions belonging to what's called the group. Right? So associated with every file is one or more groups. Right? Now, you can't actually, unless you're a system administrator, you can't actually create a group. All right? That's the username belonging to the file. This is the group name belonging to the file. Right? You'll notice that they're the same. Right? But that's actually a username. That's actually a group name. So in modern versions of Linux, every user gets a group name that's named after the user. And that's just to make dealing with certain types of permissions easier. Right? The system administrator can create other types of groups. So for example, it's possible that if you were working in CAS Lab, the system administrators could create a group called CISC220, where all students in CISC220 would belong to that group. Right? So now, if there's a group associated with a file, those are the permissions that define what the group can do with this file. Right? So this says that the group can read this file. The group cannot write to the file. The group cannot execute the file as though it were a command. World, the class of users called world is everybody else. So everybody that's not the user, everybody that's not in the group. Right? Excluding the system administrators. So these are the permissions belonging to everyone else on the system. Right? So again, the R indicates that anybody can read this file. Right? They cannot write to the file. They cannot execute the file as though it were a command. Right? So first symbol, type of file. Next 3 are the user permissions. Next 3 are the group permissions. Next 3 are the everybody else's permissions. And we can skip over these for now. Okay, so what if you want to change the permissions on a file? Right? So for example, if you have a really important file that you've created and you really don't want to overwrite it, you might remove the write permission from that file. Right? So for example, once you're done your assignment, you might choose to remove the write permission from that file if you were being paranoid, right? So that you don't change it accidentally. All right, so if you want to change permissions on a file, then the command that you probably want to use is called chmod, right? Change mode. Right? Change mod works in, there's 2 different ways that you can run the program. So the first way is that you specify the permissions using what's called an octal number. Okay, so what do I mean by that? So the first way that you can use the program is you can specify a 3-digit number to set the permissions on the file. Right? Why is it called octal? Because there's 8 different things, right? There's 8 different values that you can choose. There's 8 different combinations of the permissions, right? So read, write, and execute. Any one of those permissions can be on or off, right? So in other words, each one of those 3 things can be in one of 2 different states. What's 2 to the power 3? It's 8, right? So there's 8 different possible settings for your permissions. Right? So using the octal value 0, right? If you write that down as a binary number, that's just 0, 0, 0, right? Which is the same thing as nothing, 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 right? So the octal value 0 corresponds to no permissions on that file, right? What about the octal value 1? Well, in binary, that's just 0, 0, 1. So we're turning on, right? So the 1 indicates that the permission is on. So we're going to turn on execute permission for that file. 2 is just 0, 1, 0, right, in binary. So we're going to turn on write permission for that file. Right? 3 is 0, 1, 1. So we'll turn on write and execute permission. Right? 4 is 1, 0, 0, so read only. 5 is 1, 0, 1, so read and execute. Right? 1, 1, 0, read, write. 1, 1, 1, all permissions. Right? Anything shown in blue are the common permissions, right? It doesn't really make sense to have a file that you can execute, but you can't read, right? Because if you can't read the file, you can't execute it either, right? So that would be an unusual permission to set. Similarly, it's unusual to set the permission W, only having W. So you can write to the file, but you can't read it, right? And WX is also unusual, right? Again, you want to treat this as an executable program, but you can't read it, which means you won't be able to run it anyway, right? The other permissions are reasonable or reasonably common, right? So read only and execute only. So that would be if you had a program that you can't change, but you want to run it as a command, right? Read write, you have a program that you want to read and write to. It's not an executable program. RWX, that's a program you own that you want to be able to execute, edit, and read, right? Okay, now there's 3 groups of permissions for every file, right? So there's the user permissions, there are the group permissions, and there are the everybody else permissions. So you specify 3 octal values to change mode, right? So for example, change mode 400, right? Just look up what the numbers mean. 4 means read only, 0 means nothing, right? So this says for the file1.txt, give the user read access and take away all other permissions from all the users. So in Linux, I guess we'll just go to that directory, CISC220 notes - scripts, and then permissions. Okay, so I've got this file called file1, right? You can see that it has, that I have read, write, and execute permission on that file. Group has read and execute permissions on the file, right? And the world, everybody else, has no permissions on that file, right? If I use changed-mod 400 file1 and then list the file again, right? You can see that the user now only has read permission, right? And everybody else has no permissions on the file. Right? 444 gives read permission to everybody and removes all other permissions. Right? 755 gives the user all permissions. It gives everybody else read and execute permissions on the file. Right? Okay, so that's using an octal value to run change mod. I think most system administrators probably use the octal values. So people who do this a lot will memorize what the octal values mean and then do it that way, right? You can also figure out what it means by converting the number to binary. But most people don't like converting numbers to binary. So that might not be so useful. For the average user, it's slightly easier to remember the symbolic way to drive the program. So you can use the symbol U to mean the user, right? So change mod U means change the permissions for the current user, right? G means change the permissions for the group. O means change permissions for everybody else. A means change permissions for everybody all at once. Right? Now to add a permission, you use the symbol plus. Whoops, sorry. Right? So plus will add a permission. Minus will subtract a permission. And equals will assign a permission. Right? And then finally, R, W, and X are read, write, and execute. So what you do is you combine these 3 things. You take one symbol from here, one or more symbols from here, one symbol from here, and then one or more symbols from here. So for example, let's look at the second one. We'll do the first one in a second. So change mod U plus W means, fname means, for the user, add write permission to that file name. Right? Now when using plus and minus, you have to remember that it's adding this permission. It's not changing anything else though. Right? So U plus W means give the user write permission. If the user, it doesn't change the read permission or the execute permission for the user, And it doesn't change the permissions for any other user. Right? So this simply means add write permission to the user for that file. U minus X means take away execute permission for that file, but don't change anything else. Right? If you want to change a bunch of things at once, that's when you want to use equals. Right? So if I want to give everybody read, write, and execute permission, A equals RWX is what you want to do. Right? So that will actually assign those permissions for all users. Right? And finally, if you want to, you can combine these things using comma. Right? So I can set the permissions for the user, right? Comma for the group, comma for everybody else, right? For other. Right? So U plus X means give the user execute permission, right? Or add execute permission for the user, right? Make the group permissions read and execute, right? So take away write permission for that file name there, right? And then don't touch the permissions for everybody else. All right, so that's how you change or modify permissions on files. Any questions about that? It's basically just the one command that you need to know how to use, right? So just change mod. Let me just scroll through the notebook to see if there's anything else to cover. No, so the group, yeah, so the notebook just has a bunch of examples in it. So you just run the examples and then look at the output of ls to see what the effect of the command is. Right. All right, what about streams? Okay, so a stream, we talked about this briefly in a previous lecture. A stream in Unix, or a data stream in Unix, is just a sequence of bytes. Right? And so the way Unix commands work, they read streams of data, and they write streams of data. Oop, oop, okay. So in Unix, there are 3 standard streams that every terminal gets. So a terminal, when you fire up your terminal program, is guaranteed to have 3 streams. Right? So standard input is the stream from which data can be read. Right? So on a Unix-like system, when you fire up a terminal, that terminal is normally connected to the keyboard by default. Right? So your keyboard is connected to standard input. Right? When you type stuff into the keyboard, that goes through the standard input stream. Some program can read that stream if it wants. Standard output is the stream to which normal data gets written. Right? So on a Unix-like system, standard output normally automatically gets hooked up to your terminal by default. Right? So in other words, when a program writes something to standard out, it shows up in your terminal program. Standard error is the stream to which error or diagnostic output is written. Right? So that's the 3rd standard stream. And on Unix-like systems, standard error normally goes to the terminal by default. Right? So when you open up your terminal, you have 3 streams. Standard input goes from is hooked up to the keyboard. Standard out and standard error go to the terminal. Right? Each one of those streams has a number. Right? The number 0 is associated with standard in. The number 1 is associated with standard out. The number 2 is standard error. Right? It's possible for the user to create other streams. Right? But we're not actually going to be doing that for the bash part of the course. But it can be done. Right? So these numbers 0, 1, and 2, they're just called, their name is called a file descriptor. Right? That's just the name that was given to them. Right? Okay, so pipelines. Where's redirection? Hang on. Okay, we're going to do that in a second. Okay, so pipelines, we've seen these as well. Right? So in a pipeline, input can come from standard input. Oh, hang on just a second here. Let me just flip to the notebook corresponding to this one. Streams, redirections. I think we talked about, sorry, just let me quickly check if I talk about redirecting in this set of, oh, I do. Okay, so we'll talk about that. We'll get to that in a second. Okay, so a pipeline. So commands in Linux are like segments of a pipe. Right? So imagine you've got this pipe. Right? One end of the pipe is open, the other end of the pipe is open, right? So at the one end, that's where your input comes in, right? That goes through a command, that's your pipe, right? And at the exit of the pipe, that's where your output goes, right? Normally input comes from, standard input is your keyboard, standard output is your terminal. Right? So input flows in one end of the pipe, and it comes out the other end of the pipe. Right? So input can take the form of a command line argument. Right? So if my command is ls, right, then ls/bin, right, that /bin goes into the input of the ls command. Right? So that's a command line argument. Right? That's treated as input to the program. Right? And then ls outputs the contents of the outputs the listing of the directory root bin to standard output. Right? Some commands will read standard input for their input. Right? So for example, the sort program, if you run it, if you just type sort and then press enter, your terminal will go to the next line, and then the cursor will just blink. So it's waiting for you to start typing stuff in. Right? So in other words, the sort program can in fact read from standard input if there's no command line arguments. So for example, right? So if I just type sort, right, the terminal goes to the next line, and now the cursor blinks. Right? So I don't have control over the, I can't enter another command. Right? The terminal is waiting for you to start typing stuff in. Right? So I don't remember what I have on the slide. I'm just going to type zebra, antelope, dog. Right? Okay, so there's my standard input, and then you might wonder, okay, so how do I tell sort that I'm done entering stuff on standard input? Right? And so the answer is you press Control D. So Control and then the D, Enter and then Control D. Right? So pressing Control D indicates the end of standard input. So dog, then enter, then Control D, right? Marks the end of standard input. So now the sort command reads everything that's on standard input. So it reads zebra, antelope, and dog, and then it does its thing, right? So sort sorts lines of text alphabetically, right? And then writes the result of standard output. So it writes antelope, dog, and zebra. Right? So sort's one of these programs that can in fact read standard in. Not every program, I guess most commands don't actually read standard input. Right? Most commands expect command line arguments, or they want, most commands expect standard command line arguments of some kind. Right? So sort reads standard in and then writes to standard out. Right? Calsay will also read standard in. Right? So if you just type calsay and then press enter, right? Again, the terminal will go to the next line, the cursor will blink, it's waiting for you to type in some text. You type in some text, press enter, and then Control D, and then calsay will print out a cow that says whatever it is you asked it to. Right? So calsay, right, cursor blinks, it's waiting for some input, so hello. Right? Enter, Control D, right? And so now the calsay program reads the text that you entered in standard input, the keyboard, right? Does its thing and sends the output to standard out, right? The terminal. Okay, so command output usually goes to standard output, right? So sort, if you give it a list of words to sort, it'll write the output to standard out. Right? ls, oh, wait. If your program encounters an error, right, and your program and the command that you're using is the implementation of the command is written well, right, then any error output will go to the standard error stream, right? So whatever output that ls generates in this case, right, there is no directory called root bin zzz. So ls prints an error statement, right, and it prints that to standard output. To standard error. Right? Now, standard error and standard output, they happen to be directed to the same place in most for a standard terminal. The ls command can write to both standard in and standard out. So, for example, okay, so let's run. So ls root bin. Root bin zzz. So there's no file called zzz, right? So that writes to standard error. Right? So that actually went to standard error. It looks like it looks like it went to the terminal, so you might think it went to standard input, but that's not true. It actually went to standard error, right? If I ask ls for the contents of two things, though, so if I ask it to list information about the zip program in that directory, right? So that writes to standard output. Right? Now if I ask it for both, right? One of the outputs went to standard out. The error message went to standard error. Okay? So a command can write to both streams at the same time. Right? So don't assume that everything went to standard error or to standard out. Right? Okay, now as a user, you can change where this stuff goes. Right? So a user can change where a command gets its input from, and it can change where the output gets sent. Right? And the way you do this is with what's called redirection. Right? So if I redirect standard output or standard error, right, I can redirect the contents to a file. Right? So in other words, I can take the output of a program and send it to a file. Or I can take the output that went to standard output and send that to a file. I can take the output that went to standard error and send that to a possibly different file. Right? You can also redirect standard in. So instead of having a program read the keyboard, you can instruct the program to read from somewhere else, right? Some other input stream. Okay, so redirecting standard output and standard error are the more common use cases. It's a little bit, it's less common to redirect standard in. So to redirect standard output, you place this funny syntax somewhere in the command. So this says after the command and its arguments. That's not actually true. You can place this anywhere in a command. Right? So you write 1 greater than, and then the name of the file where you want to send standard output to. Right? So the 1, that's your file descriptor. Right? Remember, number 1 corresponds to standard out. Right? The greater than symbol is the redirection symbol. Right? So what that does is it runs the command, takes the output of that command, and writes it to that file. Right? If that file doesn't exist, it makes that file for you. If the file does exist, it overwrites the file. Right? So for example, if I want to list all the files, including the hidden ones in a directory, I can use ls minus big A. Right? And then instead of printing that to the screen, I want to save that into the directory files.txt, into the file files.txt. Right? So you can write ls minus A, 1 greater than files.txt. Right? So there's ls minus A. This is not the most interesting. Let me go up a directory. ls minus big A. Right? So there's a bunch of files here. Right? So if I, instead of printing that, I want to save that to a file. 1 greater than files.txt. Right? Notice that there's no output. Right? Why is there no output? Because I redirected whatever was going to standard out. I sent it somewhere else. Right? I sent it to the file files.txt. Files.txt. Thank you. Right? And so there you can see the output of the ls command went to this file instead. Now notice that the output of ls, right, the stuff that gets written to the file is not the same thing that gets printed to the screen. Right? That's what got printed to the screen when I ran ls minus A. Right? When you write to a file, and when you redirect the output to a file, you get 1 file name per line, unless the file name happens to have the new line character in it, in which case your file name gets printed to as many lines as you have new lines in the file. Right? Okay, so redirecting standard out is so common that you don't need to write the 1. Right? So instead of writing the 1, you just leave it off, and you just use the greater than symbol. That will always redirect standard out. Right? So that command does the exact same thing. Any command that sends its output to standard output can have its output redirected to a file. Right? So I can run the calsave program and save the output of that program in the file called mu.txt if I wanted to. And if you don't want to overwrite a file, instead you want to add to the end of the file or append to the file, you use 2 greater than signs. Right? Okay, so if you want to redirect standard error, then it's the exact same thing. It's just now you have to specify which stream are you redirecting, right? So the standard error is stream number 2. So you always write 2 greater than to redirect standard error. Right? So if I want to redirect the error message, when I do ls root bin zzz to the file error.txt, then you just write that 2 greater than error.txt. Right? That will produce no output, and it will write the error message to error.txt. Right? So again, so remember again that a command can write to both standard in and standard out at the standard output and standard error at the same time. Right? So if I go back and run this command here, right? So remember this command here is going to list the file bin.zip, and then it's going to print out an error message because there's no directory called bin.zz. Right? I'm going to take that error message and I'm going to redirect that to a file called error.txt. Right? Now when you do this, you're only going to see root bin /zip here. Right? So in other words, you get standard output still, right? That still goes to your terminal. But standard error now went to this file called error.txt. Right? And if you look at what's in there, you'll see that ls cannot access the file bin.zz. Right? No such file exists. Right? So you can redirect. So there, that really does show that that particular command using ls really did write to 2 streams when the command ran. Right? You can redirect both streams if you want to. Right? So I can run that command again. I can take standard output, send it to files.txt. I can take standard error, send that to error.txt. Right? So you're allowed to redirect both streams. Right? That's redirecting standard output. That's redirecting standard error. You can redirect standard input, but it's usually not needed. So to redirect standard input, it's the less than sign, right, instead of the greater than sign. Right? So the full the full syntax to redirect standard output is file descriptor, so that's 0, corresponds to standard in. Right? Less than, and then the name of the file where you want to read, or the name of the file that you want to use as input. Right? So most commands already accept files as inputs, so you almost never have to do this. Right? You can use redirection if you want to, but usually there's no point. So for example, if I had a file called unsorted.txt, right, I can redirect standard input to read from unsorted.txt instead. Right? So this will just sort whatever's in the file unsorted.txt. Right? Now sort reads a file anyway, so you would normally not write the 0 less than here. Right? There's only one input. There's only one standard input. So to redirect standard input, you don't actually need the 0. Right? You can just use the less than sign. And again, you can redirect all 3 streams if you want to. Right? If you know that your program outputs to more than 3 streams, you can redirect all the streams. Right? So you can redirect any of the streams for a given command. Pipelines. Okay, so commands accept inputs and have outputs. So can you connect the output of a command to the input of a second command? The answer is yes. Right? We've seen this. We know that it's just a pipeline. Right? So this is why I said at the beginning of the lecture that commands resemble segments of a pipe. Right? So if I join 2 commands together, that's taking the output of ls, right, and sending that as the input to less. Right? How do you join 2 commands together? In a pipeline, it's just the vertical bar. Right? So ls root bin, right, run the ls command, send the output, send standard output to the standard input of less. Right? Fortune, vertical bar causa means run the fortune program, right? Take its standard output and direct it to the standard input of causa. Right? And you can connect as many commands as you want. Right? So you can write very long pipelines, although it's unusual, but you can if you want to. Right? So you can connect as many of these together as you like. Right? So this command here is going to list all the files in bin and user bin. Right? It's going to send the results to sort, and then sort's going to send its output to less. Right? So it turns out on my system there's lots of files in bin and user bin. So if we do this, user bin, right? So if I just do that, it's going to spit out a bazillion files, right? If I pipe that output to sort, it's going to sort all that output. And when you sort all that output, you're going to notice that almost every file is duplicated twice, which means that it shows up in both bin and in user bin, right? And that's just because that's the way it works on Linux, in this particular installation of Linux, right? And then finally, if I actually want to look at all these files, because there were a lot of them, what happened? Oh, there we go. Okay. Boop, boop, boop. I can sort them, and then I can send them to a program like less or more, right? And now I can look at them one page at a time, right? Notice you've got a program called square bracket, right? That actually corresponds to a command in Linux, right? So there's a command that's called square bracket in Linux, right? And now I can page through the output one page at a time if you wanted to, right? Because that's what the less program lets you do. Okay, and then there's just a bunch of examples that you can work through, right? So if you wanted to count how many files there are in both directories, you can use this command called wc, right? So wc is word count, occasionally useful. Right, so wc, print new line word and byte counts for each file, right? So in other words, it counts the number of new lines, it can count the number of words, it can count the number of bytes that are in a file, right? So if I list all the files in these two directories, send them to sort, right? Send the output of sort to word count will count the number of lines that are produced by sort, right? Minus L counts just the lines, right? So that'll print out the number of files in both directories, assuming there's no weird file names in those two directories, right? So instead of sending it to less, I'm going to send it to word count, right? And now it says, oh, there's 3,623 files in those two directories, right? Bin and user bin contain many of the commands that are available to you in Linux, right? So you can see there's quite a lot of them, right? How many unique files are there in total? Right? So you can use this command called unique to help you with that. Right? So what does unique do? Unique reports or omits repeated lines. Right? So in other words, if you have two lines that are the same side by side, so they have to be adjacent in the file, unique can remove all of the repeated lines. Right? They have to be adjacent though, right? Which is why you have to sort first. Right? So we want to count the number of unique files. You just change this pipeline. Right? So add in a call to unique after sort. And so there's 1,813 unique file names in those two directories, right? Roughly half. Right? Now if you want to note how many of those are actually duplicated, well, I can pass in this option to unique. Right? So -d asks unique for the number of duplicated files, right? In other words, keep only the duplicated ones, I think. The answer is yes, right? So 1,810 of the 1,813 unique names are in fact duplicated. Sorry, 1,810 of the names are actually duplicated. So in fact, there's 3 unique names in the two directories. Or 3 names that are not duplicated in both directories, sorry. Right? Okay, so there's your pipeline. So that now gets you everything that you need to know to do the assignment. Because right? there is a couple of questions that ask you to write a pipeline, and there is a question that asks you to do redirection. All right, any questions? If you're just looking at the notebooks are complete, so they contain basically everything that were in the PowerPoint slides, and you can run the examples directly from the notebooks.